Where was I going with this now? Oh yeah, I was with the notation here. If you want the area underneath this curve from 0 to 6, and you know that this is, well, we'll just call it f of x, whatever. It was negative 0.2 x squared or something or other. But if you want the area underneath here, the integral from 0 to 6, if you want the area from 0 to 6, you talk about the integral from 0 to 6 of f of x with respect to x here. This represents the area. That represents that area. This is a definite integral with those two numbers there. Without this, what you're going to write looks like some expression, an antiderivative, plus any possible constant. With those values there, that's... Okay, so that's what this expression is here. Yeah. Okay, we're looking at a simple one here. This is x. This is about the simplest function you can, well, not quite the simplest, but this straight line here, y equals x.
Oh, it's hard to draw straight line.
Some of you have already made this connection, but we will use this anyways. We want to know what this has to do with the area and with indefinite integrals, right? So we've got area underneath a curve here. What numbers do I want here? Let's say here's A. No, let's just use A and B here. Here's A and here's B. Right? We want the area underneath there from A to B. The area underneath there we're writing as this. F of x dx, right? That's the expression for that area, the definite integral, right? And how did you say you find that area when it happens to be a triangle here? Well, you can use a trapezoid, but we're going to have to use the two triangle subtraction method to see the connection here. This was x dx here, right? That's the specific function here. I just put it in. Okay. If you want, you can do big triangle minus little triangle, right? Big triangle minus this little triangle right there. The two areas subtracted. So this blue area here minus this yellow area. I should have made this green over here, I guess. No, I should have not made it green. If you subtract those two areas, what's the area of the big triangle? Well, what's this distance here? Big triangle it's B here for big. And it's also B there, right? Because it's y equals x in this particular case. So it's a half B squared, right? And what's the little triangle? 1/2 A squared. So the area of this yellow part in here is, well, it's 1/2 B squared minus 1/2 A squared, right? It's the leftover part. This is the area. Whatever that happens to be. It happens to be that in this particular case here. What's the indefinite integral have to do with this? What's the indefinite integral of, if you have a function that's y equals x, what's the indefinite integral of that? What's the integral of x dx? 1/2 x squared, right? If you do 1/2 x squared, evaluated at the two values you want and subtract them, that gives you the area underneath there, okay? If you do 1/2 x squared, that happens to be one antiderivative, right? Like there's this plus c here, because it could be anything, right? Remember, it could be any constant added on there. But if I was to subtract this here, if I do 1/2 x squared evaluated for b, I get 1/2 b squared, right? And if I subtract, I'm going to say evaluated at b, except that looks like a plus b because my t looks like a plus. and minus 1/2 x squared evaluated at a. If you subtract those two things, you get the same thing here, half b squared minus a half a squared. You were going to find the values for these things by subtracting two areas. Then it doesn't even matter if you put a constant there, because if I said, well, we don't know, it could be any constant here. The indefinite integral can be any constant. If I said if I wanted to use a half x squared plus 90,000 as my function, it shifts it, but when you subtract it, what happens? It gets canceled out, right? If you're using this, what it is, right? If you're using that as the thing it is, and you subtract it, it gets canceled out. You get the same answer no matter what. It doesn't matter what antiderivative you use. You probably are going to use the simplest one without any constant added on. This happened to be one where you can see geometrically the areas and how they connect to this, but it's going to be the same either way. The thing that we used here was any antiderivative. This is some antiderivative of the function, okay, of x, which is the function. So what do we do there? We said if we want the area under, I think we need more space is my problem writing all over the place here. If you want the area under f of x from A to B. If you want the area under some curve like this from A to B, so you want this area in here. If you want that area from A to B, and you can color it better than that, as long as you know an antiderivative of this function, which here they use capital F, you can find it by evaluating any antiderivative of f, okay, by evaluating any antiderivative of f of x. Here they're calling it capital F. I don't know, f of x. For b minus the same thing evaluated at a, right? For a and b, I guess I should say it the right way around, b and a, and subtract them, right? And subtract. You subtract the two because then any constant you add on is going to disappear. So up above there where it's written out, where you can write it out, this is this kind of symbolic way of doing this, right? If this is any antiderivative of this, okay? If capital F is an antiderivative, in other words, like if this is x to the third, this is 1/4 x to the fourth, right? For example here. All you have to do is evaluate this at B and subtract that same thing evaluated at A. That's how you evaluate integrals. In the textbook, they call this the Fundamental Theorem of Calculus Part 2. Sometimes this is called the integral evaluation formula or something like that. If you connect it to areas for yourself, you'll understand why it works. Now, we used simple examples to see why it works. We haven't gone through and done some formal proof or anything like that, but it's easiest, I think, if you have that intuitive understanding from a real example with triangles or whatever. You could use other functions where it's something you could calculate the area from geometrically and see that it works the same way. This is saying that you can use, this connects the definite integral here with indefinite integrals. You can use an antiderivative or the indefinite integral to calculate area under curves. It's fundamental theorem of calculus. It starts to tie together derivatives and integrals. Probably you wouldn't have ever before you started this. If you read in the textbook, they try to make like they're very excited about this because it's a very exciting thing. We have to save this for another video.